This is the video of the Unit 1 study guide for Math 7. Section 1 is about modeling integer operations, so we're going to model the operations with integers. Remember that modeling and actually doing the work are the same thing. If you ever want to check to see if your model is correct, first determine if you got the correct solution when you simplify your expression. Then you'll know if your actual model is accurate. In this case, there's a key. Okay, there's a key. Let's pay attention to question number 1. We know it's an addition problem. This is 1, 2, 3, 4 positives, and then 3 negatives, so 4 positives plus 3 negatives. Over here, number 2 says draw a picture in the box to model 4, take away 5. It doesn't say how, but assuming that there's no line, it's going to be integer chips. So we'll start with the first number, which is 4. So I'll draw 4 positives, 1, 2, 3, 4. Then it says to take away 5 positives. The problem is that there's only 4 positives to take away. What I'm going to have to do is do a thing called a zero pair. When I add a zero pair, the value in this box is still 4. Because it's 1, 2, 3, 4, and then this together is 0. So it's 4 and then nothing, so it's still 4. But I do have enough positives in the box to take away 5 of them. 1, 2, 3, 4, 5 have been taken away. I'm left with -1. Can I confirm that that's the right answer? Let's see. 4 minus 5, I do keep, change, change. They fight the negative one by 1, which is the same thing over there. So I know that my check, this is correct, because I checked it doing it that way. Question 3 asked us to model on a box to model 6 plus -2. I'll start with 6. 1, 2, 3, 4, 5, 6. I'll add 2 negatives. If you want, you could cancel these or circle these. We're left with 4 positives, which if you check, the positives win by 4. That's what you should have ended up with. But that's what it should look like when you model on with integer chips. Use the number line to model 9 plus -4. I start the first number, just like I start 6 here. Start the first number, which is 9. Here's a tip for you. You know what the answer is going to be. These two numbers fight. The positives win by 5. So I know my answer is going to be at 5. I'm going to end up at 5. Either way, let's walk through it. If I add negatives, when I add negatives, it's going to go to the left. So I'm going to go to the left 1, 2, 3, 4 times, draw an arrow. So I know that's where I'm going. 5 is what I wanted, so 5 is my correct answer. That's how I would model it. Use the number line to model again. -5 minus -7. I'll start with the first number, which is -5. Start at -5. If we want to think about it and talk it out, -5 minus -7 is keep, change, change. They fight. The positive win by 2. I'm going to end up at 2. So this is where I should end up. So let's go through it. If I take away negatives, I'm losing negatives. Losing negatives means I'm going to go to the right. 1, 2, 3, 4, 5, 6, 7. Where do I end up at? 2. Just like I thought I was going to end up at. 6 asks you to write a multiplication problem to represent the model to the right. 2 answers that we would have accepted. We could say that there's 2 rows of 3 negatives, so 2 -3s. Or we could say that there's 1, 2, 3 rows of -2. In either event, this product is -6. Yeah, there are 6 negatives. This product is -6. Yeah, there are 6 negatives. Either one of these would be acceptable for the model of multiplication on the right. 7 says to draw a picture to model -9 divided by 3. Start with 9 negatives. A little too big. 1, 2, 3, 4, 5, 6, 7, 8, 9. Starting with 9 negatives. I'm now going to divide it into 3 groups. That divisor says how many groups. I need 3 groups. I have 3 equal groups with 3 negatives in each of them. So that's how I divide into 3 equal groups. Number 8 says to write the addition problem. I again know it's addition because it says addition. It's 1, 2, 3, 4, 5, 6 positives plus 3 negatives. That easy. Draw a picture in the box to model -4. Start with 4 negatives. Start with the first number. 1, 2, 3, 4. And it says to take away a positive. Well, guess what? I have no positives. That's a 0 pair. That's 2 0 pairs. That's 3. That's 4. That's 5. That's 6, that's 7, and that's 8 zero pairs. So now I have 4 and a whole bunch of nothings, which means I still have 4. So now I have 8 positives. I'm going to take away 8 positives. Oh, there's 1, 2, 3, 4, 5, 6, 7, 8 positives. What am I left with? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 negatives. I'm left with 12 negatives. Is that what I should have gotten? Well, let's see. Negative 4 minus 8 is keep, change, change. They work together. That's negative 12. So this is verifying, checking that my model is in fact correct. Draw a picture to model negative 6 plus negative 2. This is about as easy as it's going to get. Start with 6 negatives. 1, 2, 3, 4, 5, 6. I'm going to add 2 negatives. And I'm left with 8 negatives, which is what this sum would be. Number 11 says to model 8, take away 12. Start at 8. Take away 12. If I'm taking away 12 positives, I'm going to go to the left because I'm taking away positives. I'm going to go away from the positives because I'm taking away positives. 8 minus 12 is keep, change, change. They fight. The negatives win by 4. So that's where I should end up. But let's check anyway. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because the number's 12. 12 times, this is negative 5, so this is negative 4, just like we thought we'd end up at. Number 12 says to use the number line to model negative 2. We'll start at negative 2. Take away 7 positives. If I take away 7 positives, I'm going away from the positives. 1, 2, 3, 4, 5, 6, 7. Looks like I'm at negative 9. Let's check this. Negative 2 minus 7, keep, change, change. They work together. The negatives win by 9, just like I thought. I ended up at negative 9. Number 13 is a little bit tricky, one we don't see too often. It is a multiplication problem. It's going to the left. 1, 2, 3, 4, 5, 6, 7, 8 to the left. And then up 1, 2, 3, 4. So left 8, up 4, negative 8 times 4. And the last modeling question, modeling on number line, 2 times 4 is 2 fourths. Start at 0. That's 1 4. 1, 2, 3. That's 2 fourths. What do I end up with? 10, 9, 8. Which is what you'd think. 2 times 4 is 8. That's why I finished at 8. Start at 0. That's 1 4. That's a second 4. 4 and another 4 is 8. 2 4s is 8. This page just asks you to evaluate. Find the value of. Evaluate. Just going to do that real quick. 28 divided by 7 is 4. Signs are the same, positive. They fight. The negatives win by 12. We don't do subtraction, keep, change, change. They fight. The positives win by 2. 4 times 10 is 40. Signs are different, negative. 18 divided by 2 is 9. Signs are different, negative. They work together because they're both negatives. 12 negatives and 4 negatives is 16 negatives. 7, we don't do subtraction, we do keep, change, change. They work together, 18. 5 times 4 is 20. Signs are different, negative. They work together. 9 negatives and 4 negatives make 13 negatives. 12 divided by 6 is 2, not 6. 12 divided by 6 is 2. Signs are different, negative. 6 times 4 is 24. Signs are the same, positive. Two minus 14, we don't do subtraction, we do keep, change, change. They fight. The negatives win by 12. 35 divided by 5 is 7. The signs are the same, positive. We do addition. They fight. The negatives win by 11. 11 times 2 is 22. Signs are the same, positive. We don't do subtraction. Keep, change, change. 0 plus 12 is 12. That's called the additive identity. 28 divided by 7 is 4. Signs are different, negative. Negative 15 and negative 3 work together. 15 negatives and 3 negatives is 18 negatives. We don't do subtraction, we do keep, change, change. They work together, that's 18 positives. 4 times 10 is 40, signs are the same, positive. 18 divided by 2 is 9, signs are the same, positive. We do addition, they fight, the negatives win by 8. The last column, we don't do subtraction, we do keep, change, change. They fight, the positives win by 2. 5 times 4 is 20, signs are the same, positive. They fight, the negatives win by 5. 12 divided by 6 is 2, not 6. Signs are the same, positive. 6 times 4 is 24, signs are different, negative. We don't do subtraction, keep, change, change. Signs are the same, sorry, they work together, negative 16. 35 divided by 5 is 7, signs are different, negative. They work together, 18 negatives and 7 negatives is 25 negatives. 11 times 2 is 22, signs are different, negative. We don't do subtraction, keep, change, change. 0 plus anything is negative 12, that's the additive identity. Moving on to some word problems, it says Mary's team is playing Math Jeopardy. The team had 50 points, they lost 25 points for talking. They had 50, they lost 25 for talking. Then they won 100. How many points does each team have now? This is called an expression. This is the expression that represents the situation. Now that I have the expression, I can simplify the expression to get the correct answer. 50 minus 25 is 25 plus 100, which is 125 points. Number 2. In Odd Banks, Alaska, freezing temperatures and snowfall can occur in any month of the year. This is a waste of a sentence. It's junk. February is one of the coldest months with a record low of, even this doesn't matter, low of negative 32. The highest was 70. What's the difference between the high and the low? What's the difference between the high and the low? What is the difference, which is subtraction, between the high and the low? All right, well, let's plug in. You know the high was 70 minus, what's the low? Negative 32. The low was a negative 32, so it's minus a negative. That's where some of you got this wrong. If you got 38, it's because you didn't do a negative negative, which is keep, change, change. 102 degrees Fahrenheit. Mark's team is playing Math Jeopardy. The team had 215, but they lost 25 points for talking. They had 215, they lost 25 for talking. And they won 198. This is called an expression. This expression outlines represents the situation. Now, how many points do they have left? We got to actually subtract. It's 190 plus 198. Now that I've subtracted, I now do my addition. That's 388 points. In July, question number 4. In July, we went to the lake. My brother Jake jumped from a cliff that was 28 feet above sea level. He dove into the lake and grabbed the shell that's 12 feet below at the sea level at the bottom of the lake. What's the difference, which means subtraction? The difference between the starting point and the ending point. The difference between the starting point and the ending point. You can always draw a picture if that helps. There's my cliff. There's the water. And here's our diving individual. Diving into the lake. All right, so this is 28 feet above. The sea, where he's going to get it, is 12 feet below. So we know that this from here to here is 28, from here to here is 12, so obviously it's going a long distance. How can we do it mathematically? Well, the starting point was 28 minus the ending point, which is, well, 12 below, it's a negative 12. Keep, change, that's 40 feet. Just like we think. This is 28, that's 12. 28 and 12 is where he's going to dive down to. 28 and another 12. 40 feet. Moving on to properties and sequences, which is the next section. You can go ahead and start talking about different stuff. The directions say to show 3 examples of the 10 properties. One example should be numerical, in other words, numbers, 1 algebraic, and 1 abstract. So I'm not going to do all of them because they'd be fairly tedious and walk you through all of them, but I'll show you some examples. For example, the commutative property, numerical means only numbers. 4 plus 3, and I'll just put parentheses, 4 plus 3 equals 3 plus 4. That's numerical. Algebraic means it has variables. x plus y equals y plus x. And abstract, meaning a picture. A triangle plus a circle equals a circle plus a triangle. That's 3 examples of the community property of addition. I'll fill some of these out so you can see something different than the answer sheets. Here's an example of community property multiplication. 1 of each. Yes, you could have 3. Either way, it's the same idea, just with multiplication. Another example with the associative property. This associative property says who is associating, who's hanging out together. 4 is hanging out with 2. Now the order stays the same, but now 2 is hanging out with 3. The associative property is a property of exclusion. It's a bullying property. 2 was hanging out with 4 and bullying 3, and now 2 is hanging out with 3 and bullying out 4. Same thing with variables and pictures. The associative property multiplication is essentially going to be the same thing. And then so you can see here, it's all the same, but this time with multiplication stuff. Your identity is who you are. Who you are does not change. The addition property, the additive identity is when you add 0 and stay the same. When you add 0 and stay the same, that's what happens with these. That's the addition property of additive identity. The identity property of addition, or the additive identity. The identity property multiplication, or the multiplicative identity, same idea, except instead of adding 0, you multiply by 1. Negative 3 times 1 is again negative 3, is the multiplicative identity. The distributive property, also known as the whoosh-whoosh property, is where you distribute or give something out. As you can see, and I'll finish off this example. Change the color of this. I'll finish off this example. It's a whoosh-whoosh. 3 times 6 is 18. 3 times 2 is 6. We can do some variables algebraic. 2 times x minus 4 would be 2 times x is 2x. 2 times negative 4 is minus 8. That's a distributive property. And we can also certainly do it with symbols. Let's do triangle times circle minus square equals triangle times circle minus triangle times square. That's the example of the distributive property. Probably the easiest property is the multiplicative property of 0, which says if you multiply by 0, you have nothing. Let's do the inverses. The inverses are the ones that give students the most trouble. Inverse, reverse, inverse, reverse, inverse, reverse. If you give me a number to start, say 8. Let's do 18. What could I add that would be the reverse of it? Well, that would be negative 18 would be the reverse of it. 18 and a negative 18 is nothing. But I have a variable, W. What could I add that is the reverse of it? Well, that'd be negative W. If I had a symbol, let's say tornado-looking thing, what would be the opposite of tornado-looking thing that I could add? Negative tornado-looking thing, and that turns into 0. And the multiplicative inverse, similar, a little bit trickier. What can you multiply by that is the reverse? Let's start with a number. Let's do 18 again. 18 times what? Well, that's where we start talking about reciprocals. That's 1/18. Flip it upside down. That's 1. Let's do a little bit trickier with variables. Let's say h over g. What could I multiply by? Again, the reciprocal g over h. That turns to 1. And with symbols, let's start with 1 over triangle. What can I multiply 1 over triangle by? What will be the opposite, or 1? Well, that's just regular triangle. Triangle over 1. Flip it upside down. That's the multiplicative inverse. A little bit trickier than the rest, but nothing you can't handle. Let's name the properties. I add 0, stay the same. That's the additive identity. Multiply by 1, stay the same. That's the multiplicative identity. 5 plus 3, this thing, times 0 turns to 0. That's the multiplicative property of 0. 6/5 times 5, 6 times 6/5 look like they're reciprocals of each other. They turn to 1. That's the multiplicative inverse. 4 plus a negative 4, add them together, turn to 0. In other words, they're reverse of each other. That's the additive inverse, because I'm adding. 4 times 3 plus 2, and I distribute. 4 times 3 is 12. 4 times 2 is 8. That's the distributive property.
A plus B plus C equals A plus B plus C. The order stays the same, but B is hanging out with C and excluding A, and now B is hanging out with A and excluding C. That's a property of exclusion. That's the associative property of addition. 1 plus 2 plus 3 equals 1 plus 3 plus 2. Ah, the order changed. They wanted you to think that it was the associative property, but it's actually the commutative property of addition. 4 times 3 times 1 equals 4 times 3 times 1. Order stays the same. 3 is hanging out with 4, now 3 is hanging out with 1. Is the associative property of multiplication. 3 plus 4 equals 4 plus 3. Again, the commutative property of addition. The order does change as a commutative property of addition. On each of the expressions, it has been partially simplified. What's the property? Looks to me like 5 got distributed. That's the distributive property. Here, 3 stays the same. It's really important to figure out what changed. 4 and 2 switched. That's the commutative property of multiplication. Here, again, the 4 stayed the same, but 20 plus 0 turned to 20. I added 0, stayed the same. That's the additive identity. Again, the 4 stayed the same, but 5 and negative 5 turned to nothing. That's the additive inverse. Answer the following questions using complete sentences. I'm not going to use complete sentences just to quick speed this part up. Which property is used in the work shown below? Explain how you know the property was used and why you think the student used that property to simplify. All right, from here to here, it looks like 12, 4, 50, 12, 4, 50. From here to here is the associative property of addition. Why did they do that? Maybe they thought 4 and 50 was easier to add. Then they added, they just simplified, and then they just simplified. So it looks like it was the associative property of addition, then simplify, simplify to go from here to here, and simplify to go from here to here. Looks like they did the associative property of addition. Why? Why did they do that? Well, they did that because they felt that 4 and 50 might add easier. And how do I know that they did that? Because 12 and 4 were hanging out, now 4 is hanging out with 50. The order didn't change, and 12 got bullied out, so it's not working anymore. Number 2, down here, is negative 5 plus 5 plus 0 equals negative 5 plus 5, an example of the commutative property of addition. The answer is no. The commutative property changes order. The order didn't change. What happened was, see how the negative 5 is still the negative 5? So I'm going to ignore that. But 5 plus 0 turned to 5. That's the additive identity. Add 0, stay the same. So why is it not? Because the order didn't change. That's why not. 3 asks us, which example shows the inverse property of multiplication? How do you know? Well, from here to here, negative 5 and 4, 4 and negative 5, that's a commutative property of addition. How do I know? The order changed. The inverse reverses things. Negative 23 plus 23 is 0. Now that's an inverse, but it's the additive inverse, because you're adding opposites. 9 times 1/9, that turns to 1, they cancel each other out. That is the multiplicative inverse. How do I know it's the multiplicative inverse? Because it's reciprocals. 8 plus 0 turns to 8. In other words, you add 0, stay the same. It's a waste of time property. That's the additive identity. Additive identity is a waste of time property. That's it for properties. We're now going to move on to sequences. There are 2 types of sequences, arithmetic and geometric, that you're responsible for. Arithmetic is always adding. Arithmetic is always adding. Geometric is always multiplying. So you're always going to multiply. Even if it's getting smaller, you can get smaller with arithmetic by adding negative numbers. You can get smaller by geometric by multiplying by fractions, for example, times 1/2. So it says, create an example of each of them and identify the pattern. So let's do arithmetic. Let's do one. Add negative 2. We start a number, let's say 10, add a negative 2, 8. Add a negative 2, 6. Add a negative 2, 4. Add a negative 2, 2. It looks like I'm subtracting 2, but really I am adding negative 2. Let's do another geometric. Let's add a pattern. Let's multiply by, let's do this. Let's multiply by negative 2. You might think, well, that's going to make it smaller. No, it's not. Let's choose a number. Let's start with 10 again. 10 times negative 2. Well, 10 times 2 is 20, make it negative 20. All right, 20 times negative 2. 20 times 2 is 40. signs are the same, positive. 40 times 2 is 80, signs are different, negative. 80 times 2 is 160, negative times negative is positive. So multiplying by a negative just alternates it back and forth. Multiplying by a half, that would make it small. We may see something like that as we move on. Describe the pattern in each of the sequences and determine if the sequence is arithmetic, geometric, or neither of those things. Then write the next three terms. So what is the pattern? 3, 5, 9. It looks like it's getting bigger. It's getting bigger not too quickly though. Looks like it's plus 4, so it's plus 4 each time, which is arithmetic. Let's find the next three numbers. The next three terms would be 21, 25, and 29. Question 2. Looks like it's getting bigger and not too quickly, so it might be adding. Let's see, this is plus 1. That looks like it's plus 3. That looks like it's plus 5. So then 1, then 3, then 5. I guess the next one would be add 7, then add 9, then add. So you're adding by odds, or you could say add 2 more each time, which is not arithmetic, because arithmetic you add the same thing. This is changing, so it's not arithmetic. It's definitely not geometric, it's neither. So we added 5, now we add 7, that's 106. Now we add 9, that's 115. Now we add 11, that's 126. Adding is adding the same, arithmetic is adding the same thing, geometric is multiplying by the same thing. Number 3. 9.1, 8.4, 7.8. Now it's getting smaller, but not very quickly. So let's see by how much. That looks like 0.7. It got smaller. So subtracted, or really add a negative. Again, looks like it's subtract 0.7. Subtract 0.7. To me, it looks like add negative 0.7 each time, because it's getting smaller. It's always the same thing. So we want to talk about adding in terms of subtracting. It's arithmetic because it's adding the same thing. Let's find the next three terms. Next would be 6.3. After that, subtract 7/10. It would be 5.6. After that, subtract 7/10. It would be 4.9. Number 4. Question number 4 says, looks like it's getting bigger, not by too much. Looks like it's 0.2, then 0.2, then 0.2. So add 0.2. Another decimal question, which is arithmetic. Next would be 1.0. Then be 1.2, then 1.4. Not too bad, just doing decimals. Question 5 has a pattern. Now this got small and real quick. Dylan began his number pattern with 405. To determine each new number in the pattern, he performed the same operation. Which could he have done? Could he have divided by 3? Yeah, he certainly could have divided that by 3. That divided by 3 is 105. That divided by 3 is 1. So it could be divided by 3. Could he have multiplied by 3? Nah. Multiplying this by 3 would make it bigger. Could he have subtracted 270? Well, he could for there, but does he subtract 270 on the next one? Nope. And then divide by 5. Now, that divided by 5 would be 81. That's too much. So he divided by 3. Or you could multiply by 1/3. Multiply by 1/3 or divide by 3 is the same thing. Either way, A is the answer. But I want you to remember, dividing by 3, same thing as multiplying by 1/3. This is called the, well, I'll go back up and talk about it, but this is called the common ratio. Number 6, Dave states that 1, 10, 2, 20, 3, 30 is not geometric. Do you agree? Yes, I certainly agree. It's not geometric because he's not multiplying by the same number. From here to here, it's times 10. And then this is like times 1/5. And then it's times 10 again. So he's just kind of all over the place in terms of what he's trying to get to. There's no specific pattern multiplying by the same thing. There's no common ratio. One thing that was not mentioned when we talked about ratios is that when dealing with an arithmetic sequence, that number that you're adding every single time, that's called the common ratio. Sorry, it's called the common difference. Arithmetic is a common difference, and geometric is called the common ratio. You do need to know those. You will certainly see those at some point. Arithmetic, common difference. Geometric, common ratio. So if it was 2, 6, 10, 14, 18, since it's going up by 4, the common difference is 4. If it were this, let's say 200, 100, 50, 25, yada, 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 and I was getting smaller each time, the common ratio, since it's divide by 2, divide by 2, divide by 2, which is really times 1/2, the common ratio is 1/2. Another example of geometric, if it were, let's say, 3, 9, 27, 81. So in other words, times 3, times 3, times 3. The common ratio for this example would be 3, because I'm multiplying by 3 each time. That's about it for this particular unit. We had modeling and evaluating integer operations, properties, and sequences.